Okay, this is continuing field experiments in telluric transference of electric power. Today's experiment, we're out at Brookman's Park radio transmitter site. This is a site that was originally built by the BBC, British Broadcasting Corporation, in the 1920s. It was intended to move local radio out of the central transmitter in London out to a dual frequency site, which this was originally. It now broadcasts 4 frequencies. It's an AM radio station in the medium wave or the medium frequency band, and it has frequencies of 909 kilocycles at 150 kilowatts, 1089 kilocycles at 400 kilowatts, 1215 kilocycles at 125 kilowatts, and 1458 kilocycles at 125 kilowatts. So it's quite a powerful station. It's actually the most powerful around in this region of southern England, and we're going to be looking at 909 kilocycles and 1089 kilocycles today. So the experiment today is along the lines of the Crystal Radio Initiative. This is a telluric experiment started by Eric Dollard on the Energy Science Forum, where the challenge was to light a 100-watt light bulb using a Tesla transformer receiver and receiving power through the ground from local broadcast AM radio stations. So we have a suitable coil. I'm going to go into that. I'll show that in a minute. I'll go into the detail of that design of that coil on a page in my website. But this is the field experiment where we're going to see whether or not we can actually get any power out using that Tesla transformer out of the ground. So let's just take a look at what we've got here. So this is one of the radio masts as a mast antenna, as a form of monopole antenna. So it has a section above ground, the vertical mast there, which comes out in the picture, and it has a ground plane that goes, so radial wire ground plane embedded into the earth. That normally extends in the region of up to about a quarter wavelength away from the antenna. So in this case, for 1089, it would be around about 69 meters is a quarter wavelength. So at 1089 kilocycles, it's a nominally a 275 meter wavelength, and at 909 kilocycles, it's a 330 meter wavelength. So it's got a very large ground plane here, and even if some of that power, we can actually tap into some of that power using the Tesla transformer receiver, then we'll see what we can get out. Obviously, this is being a monopole. It's driven by a generator which is in the building behind me. I'll pan around just in a moment. And the connection to the antenna, there'll be a tuning hut at the bottom, and where the generator is tuned to the mast. And the emphasis on the ground plane is being very, very low resistance, so nominally probably less than about 2 ohms in a AM broadcast transmitter like this. You don't want to lose too much power in that ground plane. Of course, this is not a Tesla generator, so it is not a Tesla coil generator, which is a Tesla coil generator is designed specifically for the transformation of the transverse electromagnetic mode to the longitudinal magnetodielectric mode, which then comes from the cavity in the secondary coil down into the earth. Now this transmitter obviously is not designed for that. It's designed for radio broadcast, the transverse electromagnetic or TEM mode, which is the Hertzian component, and this is optimized. This is the actual mast there is a vertical, so it's vertically polarized, and the RF power will radiate out in all directions, and it's predominantly designed for ground wave transmission. So in other words, radio broadcast waves which travel above the ground but close to the ground, rather than the sky wave. It will also produce high incidence sky wave as well, but this form of transmitter antenna is designed predominantly for the ground wave, obviously in the surrounding region. Now that's different to the telluric wave. The ground wave and the telluric wave are not to be confused. The telluric wave where we're talking about is from a Tesla transformer, is actually under the ground. So it's through the ground. Whereas a ground wave in broadcast radio terminology is a propagating transverse electromagnetic wave which passes over the surface of the ground, so not actually so close to the ground but through the air above the ground to receiving antennas in the region. And the telluric wave, well, the telluric wave from a Tesla transformer, as we said, we're looking for the LMD mode, and in principle in Tesla's magnifying transformer setup, in principle it's possible to pass a great deal of power via telluric LMD mode between transmitter and receiver. So we're going to be using a Tesla transformer receiver and see if we can get any power out of the ground which is being dissipated into the ground by this broadcast monopole antenna. And we're looking at quite a few hundred kilowatts, so in total here there would be, if we're looking at 909 or 1089, that would be 550 kilowatts nominally coming off of this transmitter system, and that's quite a lot of power. I mean, even if there was only 1% of that getting down into the ground, away from the ground plane, that's still 5 kilowatts. It's quite a lot of power. So, especially as we're going to set up close here with the receiver, we'll see what we can receive. Now also there are a number of different antennas here. This is a mast antenna, but originally when Brookmans Park was first designed in the 1920s, it had a pair of T antennas. They are still here, still used. Let me pan around. So there is one of the masts of a T antenna, and I hope it comes out in the camera. There's the wires going across, and they'll go all the way across to the other mast, which is there behind the trees. And just behind the trees there will be a set of wires coming down which form the T. Now there's actually one here as well. I'm going to go right down. There's another T if it comes out on the camera, and those vertical wires suspended from the two masts either end are the actual vertical antenna. And it's called a T antenna. A T antenna is another form of monopole antenna. So there is also a substantial ground plane in the earth, but the T increases the capacitive loading at the top of the vertical sections, and this improves because it's electrically short. Ideally the best monopole would be a quarter wavelength above ground, but that would make it, at these kind of wavelengths, it would make it very high. It would make it unpractical really to use, to build and maintain. So it's electrically short, and by capacity loading it with wires at the top, or the T part of it, you can improve power transmission between about 3 to 6 dBs, which is quite a lot. So originally there were two. Let's go back to the mast here. You can see the That's one of the original masts, 4 masts here, originally built in the 1920s. We're going to go a bit closer and have a look at the base as well. There's some interesting things to see there. And there is another mast further over this way. I don't know if one will be able to see it. It's behind the trees there, but there's another mast with another T. And when combined, so when this T antenna and that vertical mast antenna are combined on the same frequency with different phasing, then you actually get a more directional characteristic. So originally you had 2 T antennas here, and then these vertical mast antennas were added, which also leads to directionality. So taking with the big T that I just showed you plus this mast means that more of the energy is actually going to be, radio energy is going to be directed south away from the mast and down towards London. So it makes phased correctly from the generator. For the T antenna and the vertical mast antenna, it makes for a more directional transmission. Okay, so, well, that's Brookmans Park. Brookmans Park also played a part in the Second World War of Britain, where it was used to transmit signals for Allied communication. And now, subsequently, it is still AM broadcast. It's one of the most powerful in southern England, and there are a selection of other types of broadcast here as well. You probably saw in the camera there are telecommunications dishes. I'll probably walk past those and take a little bit of picture too. Okay, so this is the introduction. I'll add a few bits as I walk back to where we're going to do the experiment, and show a few things from the mast tower as well as we go by. Okay, so here we've just moved along slightly. This is the base tuning station for one of the T antennas. We can see, I hope that comes out in the camera, there are 4 vertical wires going up from the tuning. They're all connected together, and the reason we have 4 wires going up there is the number of wires increases the capacitance of the T. So we can increase the loading by having parallel set of wires rather than just a single or double wire going up. Of course, below that is again a form of monopole. There is going to be a ground plane, usually radial copper wires into the extending out underneath the tuning. Okay, so I've moved further along the path again, and here we get another view of the one of the T antenna towers. There's the tuning station on the ground in the middle. It's got 4 vertical wires. I don't know if that'll come out in the camera. We could try zooming in. 4 vertical wires going up, and they join the T. The sun's quite bright, so it's not easy to see. And if I come round past the sun, here is the other tower. We are actually standing right at the base, or near to the base of this tower, right up there, and the wires are going across there for the top of the T. Now, so this, we're right down close to the mounting. This is one of the original towers. So I'm going to come along, actually, see if I could walk along close. It's rare that you get an opportunity to come this close to a broadcast transmitter of this power. Fortuitously, there is a public footpath that actually goes through the centre of Brookmans Park transmitter station, and you can see all of this stuff right up close, which is great. So here's one of the legs. Let's try and not get it in the sun. Let me get it that way. Try and stay out of the sun if I can. Let me just come around the other way. Okay, so that's better. This is one of the legs at the base of this enormous tower, right up there, up to the top, and we can see the huge ceramic insulators that are each of the 4 legs which insulate this tower from the ground, from Earth. Now the tower is not actually part of the antenna, but being so close to such a powerful transmitter, obviously it will, with a metal structure, is going to induce RF currents, and as a result it's going to be at a considerable potential above ground, and that would lead to loss if it was connected to ground. If you had a grounded structure here, it would be sucking quite a bit of RF energy out of the transmitter antenna and just depositing that in the ground. Those are the insulators, and we can see in the background there the other tower of a T antenna, one of the originals. And the other one it's a little bit difficult to take because it's the sun, right into the sun. Oh, I can just, there we can see the other tower in the backdrop, right in the middle of the picture there. Come around a little bit without getting the sun. Yeah, just in the backdrop. There is also a vertical mast antenna. There as well, which goes with the other T. Okay, so now we've come up a bit further along the path, and here we've got, obviously these are a new development, telecommunications dishes. There's a whole array of them here, contributing no doubt to our television and internet broadcasts. There's a whole development of these on Brookmans Park as well. And in the background there we've got an original water cooling tower for cooling the transmitters, the generators, which are in the building behind here. So behind this section there is the main building built by the BBC in the 20s, which has got the generator rooms, and what would originally, of course, it was powered by dynamos. So you produce 240 volts DC in the generator room, and then that was used then to power the various different generators that produce the high voltage for the tubes, for the heaters, and for the various ancillary electronics and control that were required at the time. Very interesting. I shall put in the write-up some of the history of Brookmans Park. There's a couple of good links online for people that have looked at the history. Very interesting place. As I said, not easy to get so close to such a powerful broadcast transmitter. That was where we were. That was the base of one of the T antenna supports. Just out of the sun here, there I can get the other, if it comes out, there's the other vertical mast antenna. Produces, phased correctly with the T antenna, produces directional, high power directional broadcast. And then we'll carry on back down this path here and I'll show you where we're going to do the experiment. We can see here, there is the mast antenna that we were looking at earlier, and I'll just pan round. There we walked past the array of telecommunications dishes, and we've got the cooling tower. We're right next to the cooling tower, and there's also the perimeter fence of the Brookmans Park site runs around here. Now, very interestingly enough, if I go into this region outside the perimeter fence here, and we have a look at this old structure here, Now this is a one of two things. It's a mounting point, a disused mounting point, and quite possibly also a grounding node. We see on the top here it's got a metal node, disused now, but the likelihood is that we've got quite a lot of metal underneath that. And that goes down into the ground. Even if it's a pipe arrangement and goes down, it might form quite a good earthing point for our experiments in this region. So rather an interesting find that. We also do have I have a ground rod with me as well, if it turns out that that is just a piece of metal on top of a piece of concrete. But we'll give it a try and see. If that were a grounded node, for whatever its purpose might have originally been, it is an ideal place for us to connect our Tesla transformer. Let's just actually go right in. Get that. Okay, so there's a close-up of that metal node. Okay, so here we've come slightly further away and we get a very good view of the various masts that we've been looking up at close. So on the right there we've got the vertical mast antenna, and then we can see on the left the two T antennas that we were up close. One of the original, the old one with the two large masts, and the newer one in the middle. Let me just zoom in on those. Two on the right are more modern, much more simple. Don't look as impressive as the big masts, but you can also see, if that comes out on the camera, I'll go in a bit more, you could see the wire strung between them and the vertical part, which is actually the radiating part of the antenna down the center, and the T capacitive loading at the top. Let's have a look at the other one. There's the modern one. The same structure. We were standing right next to that on the path. So a very good view of one half. This is one half of Brookmans Park transmitting station. The other is on the other side. Okay, so I'm back at the experimental point. We're looking at the Tesla transformer or Tesla coil receiver. I'm just going to pan around just so one can see what the lie of the land is. So down here we've got our equipment, same trolley we use on our excursions. There's the coil, going to go into that in detail in a minute, and there is the node that we're going to explore. Now let me just focus in on the node at the top. What I've done is I've attached, let's get right in on it, that's it, I've attached a copper ring using a Jubilee clip onto that node, which has got a 4mm output, and I can plug cables in. I'll just show that. I can plug a cable in, and then that can be attached to other equipment, and that should give us a good connection to the to that node. So there's a copper plate rolled round to the same diameter as the node, and then kept in place there with a Jubilee clip at the top. That's the copper half section, and then there's a Jubilee clip to keep it in place so it's solid. Okay, so if I just pan out, we come back round and we have a look now. Oh, and the transmitter masts are over there behind the tree. You can't see them, but as I said before, we are approximately 300 meters away from what would be the ground point below that vertical mast, and just under 300 meters from what would be the bottom of the vertical T over there. Okay, so we come back round. So just to recap a little, let me pan out a bit more, that's fine. So this telluric transference of electric power experiment we're today is along the lines of the Crystal Radio Initiative that Eric Dollard put on the Energy Science Forum, and that is a challenge to use a Tesla transformer, Tesla coil receiver, to power up to a 100-watt light bulb from telluric power received through the earth from a broadcast radio, and to give it the best chance possible to see whether or not that's possible. If it is, then it means that we would be able to confirm some of what Tesla was exploring 100 years ago, more than 100 years ago, in his Tesla magnifying transformer. Just to say a little bit about that, first of all, so Tesla was using a transmitting Tesla coil and a receiving Tesla coil, and Eric Dollard's done a lot of work, amongst others, on the type of transmission mode that takes place, so the longitudinal magnetodielectric mode between the transmitter and the receiver. And in principle, if that LMD mode is established correctly between the transmitter and the receiver, then large quantities of power could be transferred between the two with very low losses. So that is the principle. Tesla was, or we presume that Tesla was working towards that, and that remains very much a challenge for Tesla research to see, first of all, whether that principle is possible, and how to go about it and establish it. So the Crystal Radio Initiative was part of that exploration, that Tesla research put forward by Eric Dollard. Now obviously it's a slightly different situation. It's not the same as Tesla's TMT, because the transmitter is not a Tesla transformer. So it's not a transformer designed to take that power from the generator and with the minimum amount of losses pass the maximum amount of power into the ground as possible. That's a Tesla transformer. By coupling the TEM to the LMD mode from the primary to the secondary in a resonant cavity of the secondary, and the cavity from the high end of the secondary coil all the way down the secondary coil into the ground over whatever distance, and back out in the receiver, of course working on the basis that you've got good ground systems. So the principle is, or meant to be, that the Tesla coil transmitter is firmly connected by a large ground down to the earth, and the same at the other end. Now in this case we have a transmitter which is very firmly connected into the ground, because it's a monopole antenna, or a form of monopole antenna. It basically has a radial approximately quarter wave ground system, which will involve a lot of copper in there, and that needs to be a very low resistance ground system, or low impedance ground system, so that we don't lose too much of the transmitter power. But we are working on the basis that even a small amount of power that actually gets dissipated into the ground, we want to see whether or not our Tesla transformer receiver is able to pick any of that up. And it remains to be seen if that's possible or not, because the LMD mode, remember the transmitter is not producing a cavity with receiver on the LMD mode, so it's very much, we do this experiment and we see what we get. Might be from nothing coming out at all to, well, it'd be great if we could light a light bulb. Let's see what the result will be. So this is the coil that we're going to use. This is a dual coil. So it is designed designed specifically for the frequencies here. So let me just show what we've got. We've got the primary coil here, 8 turns at the bottom, and we've got the secondary coil mounted on top. They are actually separate parts that can be lifted off of each other. This is a modular system that I use other coils for. We'll be doing other telluric experiments at lower frequency using this coil. So it has modular sections. This secondary can be removed, and so can the primary, but I will go in that in more detail in the write-up on my page with the design of this coil. So just to say here that this, if I turn it round, we can see, let me just check that comes out in the camera. Yes, so this section of coil here is 34 turns and is connected down to the connector via this join, and that could be tuned with a top end. So if I put a telescopic aerial on the top there, let me just show that in the picture properly. There's a telescopic aerial. It's a minimum extension, but that can be extended up. Both the parallel and serial modes of the secondary coil can be tuned to 1089 kilocycles. And 1089 kilocycles is actually one of the transmitter frequencies coming out from Brookmans Park. It's nominally 400 kilowatts. I don't know how close it is to that, but that's nominally, if you look online at the details for Brookmans Park, that is what it's currently transmitting torque sport on 1089 kilocycles at 400 kilowatts. Then you've also got a second part of the coil, so an additional 7 turns here to make 41. So to connect that, you would basically disconnect from here, connect those two together. Just put that down, let me just show. So connect those two together to form part of the winding, and then we connect at the bottom here, and that forms a 41 turn coil, and that is the parallel and series mode of that secondary coil can be tuned to 909 kilocycles, which is transmitting here at nominally again 150 kilowatts, and currently transmits BBC Radio 5 Live here in the UK. So we've got a dual frequency. Now we've got quite a few turns also on when I measured this with a network analyzer in the lab. Its optimal coupling and tuning were 6 turns. 6 turns of there's nominally 8 turns there. Let me just show the primary at the other side. So here are the primary connections. Just check that comes out on the camera. Let me focus in a little bit on that. Right, so there we can see basically we've got a terminal for each turn, and by these 2 jumpers we can connect the center 2 terminals, so we can take any number of turns from any position on the coil. And I've got that currently set to 1, 2, 3, 4, 5, 6. So 6 turns at the upper end of the coil produce the best coupling coefficient between the two with the minimum damping of the Q. So that is the trade-off. That's too many turns of the primary, you're going to reduce the free resonance of the secondary and the Q goes down. Too few turns of the primary, then your coupling coefficient is quite low, and obviously the amount of power that you can get out is also reduced. So there's a trade-off between those two, and I will be going into that in detail when I talk about on the design page for this coil. Like I said, I will put all the measurements, network analyzer measurements and preliminary measurements on this coil on a write-up on my website. I don't need to go through those now. Okay, so that is the design of the coil, and so we're going to use that. We're going to put that coil over the ground node and get that connected up and then see what the results are. But before that, it will be interesting just to see, I mean, we don't actually know what the purpose of this originally was. I did do a bit of work online to see if I could look at old plans for what this might have been. but that's not so easy to find. So I'm still either saying it's either a mounting point, or it's something to do with the water system, or it's a disused ground node from a previous version of a transmitter, or an anchor point. Could be an anchor point for a cable. So I'm still believing that there's probably a fair bit of metal down into the ground, going down underneath that concrete structure, and that in itself represents a fairly good ground, and we're going to test that. We're going to see whether or not we could actually pick anything up through there just straight with an oscilloscope. So I'm going to move the camera down. I'll just do that now whilst we keep it running. I'm going to move the camera down a bit closer and come in a little bit, and I'm going to bring a handheld oscilloscope with a wire, short wire. We don't want to have too much of an aerial above ground. Just put that on. See if we can get that in the picture. Okay, so let me just check that comes out in the camera. Rather a lot of reflection off the screen. Let me see if I might actually take it off the tripod and hold the camera close to the screen so we can see what's going on. Let me just do that. Okay. Alright, that's better. I can get it in a place where one can actually see the screen. So there's the node. There's the handheld oscilloscope. It's set to 2 volts AC vertical division, and it's 200 nanoseconds per division on the horizontal. So let's now plug that in. Or first of all, we see, okay, so let's get the reflection out so we can see the screen. So there's no signal. So even with all that power being transmitted as a transverse electromagnetic wave off of those antennas, we're not picking up anything of any real significance on there. So let me try plugging it in. Let's keep the camera up. Okay, so I've now got the wire. Let me just show the wire plugged in, and we've got quite a big signal. And if we look close in at the frequency, bottom left, we can see it's around about 9, ranging between about 970 and about 1050 megacycles, kilocycles, sorry, kilohertz on the oscilloscope. So we are getting something coming off of this node. If it's forming a good ground point, even with that very short piece of wire. We just catch that nicely, keep it steady, so we can see that result. Get the reflection out. Bit difficult to get the tripod in this close, so I'm just going to hold it, and then I'm going to disconnect that again. So pull it out, drop the wire back round, and we see basically it's back to no result at all. Nothing. Obviously, if I hold the wire, I'll act as a good antenna, and we should pick something up. So there we are. I've just grabbed hold of the wire with my hand, and I can also act as an antenna for the same signal, same frequency. Let go of it. Try not so it doesn't ground, and there's nothing at all. It's just laying open on the top of this, whatever this node is. Okay, good. So I'm I'm going to set the coil up on here, and then we'll start taking some measurements. Okay, so we've set up the experiment now. We've got the Tesla transformer receiver on top of what we're using as the ground node. We looked at that earlier. We've got a Hewlett-Packard 435B power meter. That's the same one that we used in previous experiments on single wire transference of electric power, and we're going to be using that. That's coupled to a thermocouple sensor, so we're going to use that to measure power. That's power into 50 ohms, so it's a reasonably good match with the primary at the number of turns that we're using, which is 6 turns we determined is optimal. So, and we've got a variety of different grounds here. So there is obviously the ground, which is connected directly down to that terminal node on the top of the concrete. We've also put a ground rod down into the ground, a copper ground rod about 1.5 meters. I will just show you that. So if we just come round and if we look here, we zoom in on it, there is a ground rod down into the ground. It goes right down. It's quite soft, the ground's very waterlogged, so it will make a good contact. And then we also come out slightly, we also have a wire, an above ground tuning wire. That's the long wire that I use, 10 meters long, in order to retune the coil when I remove its ground connection, so we can make a comparison between the telluric wave and the radio wave. So just show the setup from this side. There's the node. At the moment we're currently connected down to that node. We've got a telescopic aerial on the top there for tuning, and I've set the secondary coil at 909 kilocycles. So that's using both the upper section of second coil and the lower connected together. We took some preliminary measurements, and that's where we get by far the best result, on 909 kilocycles. Okay, so I'm going to come back round and we'll get going with the measurements. Now, let's just get the camera back in, put it back on the tripod. Good. Okay. Alright. Now, obviously in previous telluric measurements I've done experiments using the radio. So this radio has been used before. This is a Sony ICF 2001D analog scanner from the 1980s. It's particularly sensitive, and it's good because it has a variable gain AM RF gain control. So now, because I'm actually so close to those transmitters, I'm actually approximately about a wavelength from their centre. So I'm in the near field, or approximately the near field. I'm definitely in the induction field, and when I put it on, so I'm going to put the radio on, I'm going to tune it in to 909 kilocycles, and you see it goes hard over 10 bars of signal strength. But what is in, you've got multiple programs here, so you've got mixed programs, all incident on this tuner all at the same time via induction into the tuning and IF circuits. So if I type in 1089, go there, it sounds much the same. You've got two mixed stations, or multiple, more than. There's 4 different stations being broadcast on Brookmans Park site, and that is all mixed up. Go back to 909. So this radio receiver, because we're essentially in a near field, in the induction field, we can't really use this radio receiver as a test. Its circuits are being swamped. So We can use that further away. We've used it in the telluric experiments before because it's particularly sensitive. But here we're going to have to go straight to the power meter. So what I'm going to do is, first of all, I'm going to make sure that this is connected to the terminal node on top of this piece of concrete, which it is, and this we're going to set it just slightly into the right place for the parallel mode. So the parallel mode at 909 kilocycles. I'm going to focus in on the screen. Let me bring up the screen. There we are. Alright, so let the camera settle. So we are on the 100 milliwatt range. I'm going to just turn on. I've got this connected to a remote. Let me just disconnect for a moment. And we'll check it's 0. Just come back and check, make sure that's coming out on the camera. Yes, so we've got the meter on. We're powering that from a portable power pack. I can show that so you see how it's all set up. There's the portable power pack. It produces mains from battery, and importantly enough, that also means that this piece of equipment is not connected to ground. It is floating in relation to the measurement, and since we're trying to measure power out of the ground, it's quite important that the test equipment isn't also connected to the ground. We'll either short out our result, or we might get a wrong result because of power coming through the ground system. This is RF power, remember, coming in and forming a ground loop through the test equipment. So we're set now. That's 100 milliwatts of power. We're not connected, so I'm going to reconnect, and because the coil is so sensitive, I have to move away from it in order to be able to measure. Let me just put our connection on the other side so it's stable. Or should we adjust? Get this connection system steady, and then I'll come away, and we're right up to just over 40 milliwatts. So stable between about 40 and 45 milliwatts. We're on the 100 milliwatt range. We'll just check our 0 again, just make sure our calibration is right. So we take that away, and our needle has gone back down to 0. Reconnect it, come away from the coil, between 40, 45, a little bit higher, between 40 and 50 milliwatts. Good to read some power, but 40 milliwatts is not that much when you're only 300 meters away from a 400 kilowatt transmitter. And you combine that with the other ones, you're talking over 500 kilowatts of power. And that's power into 50 ohms here. And there's a reasonable match between the primary and the input impedance of the test equipment. Okay, so what I'll do is I'm just going to tune around a little bit. Let me put it right down, detune slightly. Oh, let's push this up. That's good. We're getting closer in tuning. Let me just take the aerial off altogether. No, a little bit lower. So we are at the right parallel tuning point. That fully is about optimal, which was equivalent to our network analyzer results. There we're just over 50 milliwatts, around about 52 milliwatts of power. Okay, so we'll tune it to the series mode. So the series mode tunes with this fully extended. So we'll fully extend up. Check that. Oh, very low. So only about 5 milliwatts. I'll go down a range just to check. That's on 30 milliwatt range now. Yes, around about 5 or 6 milliwatts in the series mode. I'm just going to use an even longer aerial just to see if we can improve on that. The series mode needs the additional wire length, so I'm going to take off the BNC, put this as an SMA based aerial. It's longer, increase the wire length right out to the maximum, see what that. Okay, good. So that's even, so now tuned to the series mode, we're even higher. Oh, no, I need to put the range back. We were on 30 milliwatts, but it's gone up to now about, come away from the coil because it's very sensitive, somewhere around about 20 milliwatts. Let's go up a range, be a little bit more steady, it'd be easier to see. So the top range there, yeah, around about 20, oscillating around about 20 in the series mode. So in the series mode, let me just bring the tuning down to see if we're optimal. Come away from the aerial a bit. No, back down. Go back up again. That's definitely the best series point. Bring it all the way back down. Let's put it about halfway down, so the aerial got about halfway extended. No, still quite low, so we're off tune. So the parallel mode, remember the secondary Tesla coil has both a series and a parallel mode. Let's see how we're back to, what we're back to there. About 30 milliwatts, still detuned. Take that off altogether. Right back up over to almost 50. We'll see if we can improve that any further. So we put the BNC aerial back on. Between 50 and 60. So that's tunes back. Let me just show what we've got on top. So go up to the top of the coil. Actually, I'll just pan out a little bit. So what I was doing is I was basically adjusting the length of this at the top here, moving it up and tuning the difference between changing the wire length at the top end of the secondary coil and tuning between the parallel mode and the series resonant mode. So right down, that's the best place for the parallel mode, and it was arranged that way in the lab with the number of turns using the network analyzer. And with the aerial fully extended, let me switch, I've got a longer aerial. Right, that's the series mode, back down to about 20. I'll just show that on the camera, so it goes right up there. So that's what I was adjusting just now. We get between 50 and 60 at the parallel mode, where the impedance of the overall system is higher, and we get about 20 milliwatts at the series mode when the impedance of the system is lower. Again, we're going to take that out. Put that back on. And best position for the parallel mode. And we go back down and have a look at the power that we're measuring. Get it back in the camera again. Okay, so we're on the 100 milliwatts, sorry. If we were on 100 watts, it'd be a totally different story. We're on 100 milliwatts and we're about 52, 54, 55 milliwatts in the parallel mode, connected to this ground node. So what I'm going to do now is I'm going to disconnect the ground node, and I'm going to connect this ground node on the concrete, and I'm going to connect the ground rod that we showed earlier, keeping the series mode. So first of all, I disconnect the node, and we see it goes all the way down to 0, not tuned, and I'm going to put the ground rod in. Just connect the ground rod. Okay, connected the ground rod. I come away from the coil, and we're up to about 40. Let me just see if that can be improved by tuning. No, just making sure that the slight change of wire length at the bottom end hasn't led to a different tuning point. We just need to be clear of that. No, that's worse. I'm heading off towards the series mode. Okay, so again, the aerial in very similar position, telescopic aerial, and now we're at 40 milliwatts. And that's from the ground rod. So it's pretty clear that the ground underneath this concrete is quite good. There's probably quite a lot of metal under there going down into the ground, whether it's a support, whether it's actually a proper grounding system with copper underneath it, or whether it's actually related to this water tower in some way, and it's some kind of got some kind of pipe, metal pipe system going down there. Either way, it's a pretty good ground, and it's better than the ground rod that we just put down. Not by a massive amount. So 40 milliwatts there, and I'm going to go back again. We just check our measurement. So again, remove the ground rod. Power goes back down to 0. Plug back in our rod, and we're back up over to almost 55 milliwatts. So almost, sometimes even pushing up to almost 60 milliwatts. So a difference between, let's call it, say, around about 40 milliwatts with the single copper ground rod, or the copper coated steel ground rod that we put into the ground. We hammered it in with a mallet, and around about, say, average about 55 milliwatts with this ground system. So the interesting question is, so that power that we're now measuring is a result of the radio wave and the telluric wave. So it's the wave that's travelling straight off that antenna, and look, we're within one wavelength, so we're in an induction field. So there is an induction component as well. That radio wave is not just a transverse electromagnetic as it would be in the far field. It's a combination of induction and the radio wave coming over the ground, and then we've got the telluric, which is power being transferred under the ground, and we need to measure the proportion of each. So to do that, I've got the way I normally do this is, you can't just remove the ground. If I remove the ground off the bottom end of the coil, it's going to detune it. So I need to detach the coil, secondary coil, from ground, and I still need to retune it so that it's tuned back to the right point again. So it's tuned back to the 909 kilocycles that we're working at. So I've got a 10 meter insulated cable just laid on the ground. I'm going to put that in now. Okay, plug that in. Come away. And I'm just going to check tuning. Just just for fine tuning. This is one that I did check earlier just to make sure we were tuned in the right place. I'm just going to do a little bit of fine tuning just to make sure. I'm doing that by adjusting the length of the telescopic aerial again. Okay, so getting up close to around about 20 milliwatts. We extend that right out, see where we could get to. No, down again. So we went past the tune point. So let me go take it back down. I think it was actually best almost. No, I went past it again. So here's a bit up like so. Manual tuning here, of course. And it's very high Q coil, so small changes make a very big difference. Okay, there we are. So we're hitting close now, almost 20 milliwatts. Yep, almost at the right point. Adjusting it only by a centimetre at a time. Okay, so that seems to be about our optimum position. We're just under 20 milliwatts. So what that means is now we are receiving, or the power meter is only measuring the radio wave component. It's not measuring the telluric component. So with the telluric component we called it 55 milliwatts, and now we've got about 18. Let me put that down a range so we can measure it a little bit more accurately. 15, 16, 17, round about 16 on a more accurate range, more about 16 milliwatts from the radio wave at the parallel point, parallel resonant mode. So that's interesting, because now we've got about 3 times, just over 3 times the telluric. So the telluric is approximately 3 times stronger than the radio wave. So this system obviously optimized for receiving the LMD component. It's a Tesla transformer receiver. So properly set up, it should respond best to the LMD mode. And that's quite an interesting result, because we've got a coil right next to a very powerful broadcast radio transmitter 300 meters away, and the strongest component that this receiver could pick up is the telluric mode. You would think it would be so swamped by the radio wave at such a short distance, especially as it's in the induction field. Interesting that the telluric component is 3 times stronger. Good. So I'm going to put this back just to check our result again. So I'm going to remove the surface wire for the tuning of the coil. Again, we should just go down to 0 because it's detuned. And I'm going to put back the ground, put it back to our optimum tune point, and see where we go back to. Just over 50 milliwatts. So consistent with Wattme. So that 50 milliwatts is the combination of the radio wave and the telluric wave together. And the best grounded point that we had was this unusual ground node that we discovered in this area at Brookmans Park. Okay, so those are power measurements. So if we put it into context, it's still not a lot of power. So 50 milliwatts of power coming out there into a 50 ohm load, and we're only 300 meters away from a combined over 500 kilowatt transmitter. It's very unlikely that we're going to be able to light anything certainly, probably we're not going to be able to light a 100-watt light bulb, as with the Crystal Radio Initiative. Okay, I just paused the video there. We had a helicopter just fly over, so it was rather a lot of background noise. That's passed over, so what we're going to do now is we're going to see if we can actually light something at all. Probably 50 milliwatts is just about enough to light an LED, I should think. So let's unplug the system first of all. We can see also the effect that I have when I get close to it. Q's so high, damps it right down. So let me disconnect. Yep, disconnect the power meter. I'm just going to put 2 and let's see. Got an LED here. Doesn't matter which way it is round because yes. So the LED lights up. Let's see if I can get that in the camera. That's falling down. Right, that's up. Let's see if it comes out. Let me adjust. Okay, so there, yes, you can see it. There's the LED. So we were able to light one LED, 500 kilowatts. See if I take it away, damp the coil down, it all disappears. Goes off, just running my hand on the coil. Obviously doesn't affect it on the primary, it does on the secondary, where all the high Q, where it's tuned. Okay, so an LED. We could also try, let's see, I've got a small neon bulb here. Put a small neon bulb in. First of all, I could try the neon bulb up the top of the coil. No, there's no real tension on the coil. It's not receiving much power. Okay, so that's a, let's turn it up. That's a small neon bulb. Let's just get that in the picture. And that's not lit at all. Nothing on the neon bulb, that's a very small neon bulb. Just to curiosity, I'm going to take that out and I am going to try putting a real bulb in. So let's plug this is a 5 watt standard bulb. Let's adjust the camera. Okay, so there we are, not lit. We'll try tuning. Just take it close to the series point, just see if that makes any difference. No, still not lit. So a 5 watt incandescent bulb whose impedance is a reasonable match because it's a mains bulb, so its impedance is not too low, but we can't see any detectable light from that, not even a slight glimmer from there. So we're going to take that out and I'm going to put in a neon, very low power neon. See how that goes. This is a 3 watt neon. I'm just going to pause again because we've got another aircraft going over. Okay, so the aircraft has passed over. I've just carried on with the experiment again, and that is with a 3 watt neon, and again there's no glow coming off of there at all. So there's no real significant tension on the coil. We would expect to light these, we would need to have quite a significant tension across the secondary. So from the base of, let me just pan out a little so I can show what I mean. So to light a 5-watt incandescent bulb, the amount of tension between the bottom of the secondary coil and the top of the secondary coil is considerable, and it needs to be at least a few kilovolts between those, and then that is going to transform into the primary enough power to actually light, even with the with a neon, even to get a glow from it. There's very little power dissipated even with a small glow, but the tension across this coil is very low. If I put the LED next to it, there's not going to be any real tension. If I attach the LED at the top, no, there's no real tension. If I look for my little neon, I'll put it right down here. My little neon would give a little glow from the top. There's no glow from the neon. So the tension across the secondary coil isn't anywhere near enough for us to be able to transform that power from the LMD mode, the longitudinal mode, to the transverse mode in the primary. Remember, primary is the TEM or transverse part of a Tesla coil, and the LMD mode, if it's set up correctly, transformed in the secondary. Okay, so I don't think today we're going to be able to light a 100-watt light bulb. The most that we could light was the LED. 50 milliwatts of power we measured here, of which about 35 of that is telluric. Is coming through the telluric channel. Let's just put our LED back there. Yeah, the LED was lit, but we were able to light something. Let's get that so that it stays in place. It won't this time. Just hold that. So there is enough radiant across the secondary to light the LED, but not sufficient tension to light any other type of incandescent bulb. We'll just check that everything's still set in the same place. Let's put the power meter back on. Obviously I can light that LED also without the telluric component. So if we think about it, I had 17 milliwatts of power coming out just from the radio wave. That's enough for me to light that LED just from the radio wave component, and that is actually what happens. The 35 milliwatts coming out from the telluric, and here we are, we're back again. Oh, let me adjust so that we can see the meter. I've reconnected the power meter, and we're back, combined radio and telluric, just over 50 milliwatts. So we were able to pick up power. If we compare it to the single wire, to the telluric experiment that I did a comparison between a 30-meter single wire and a telluric 18-meter telluric channel at the lab. By the time you add the 4 meters of the grounding wire at each end, then you were ending up at around 26 meters for the telluric channel. Then the powers that we were measuring there, we were putting 400 watts in, and we were receiving about 70 to 80 milliwatts of power. And that was in a situation where they were both Tesla transformers. So the transmitter was a Tesla transformer, and the receiver was a Tesla transformer as well. So it was a TMT system, Tesla's magnifying transformer setup. I'm just going to pause again because of aircraft. Okay, so that aircraft just went over. So in that situation, we had a TMT system. Here, this is not a TMT system. This is a broadcast radio transmitter designed to maximize the ground wave transmission of the transverse electromagnetic mode above the surface of the ground to receiver in all directions. Goes out radially from the monopole antenna, all directions to receivers in the local area. Serves London and surrounding home counties and surrounding area. It is not designed as a Tesla transformer to transform the transverse mode to the longitudinal mode and then to transfer that to a Tesla receiver. So I think it's very clear we're right next to a 500 kilowatt transmitter, and we were able to get about 50 milliwatts out using a good ground system. There's no reason to think that this ground system is not reasonable. If there was a very large ground, if we were on top of a large radially with lots of copper buried in the ground, we might expect to get a bit more power out. But given the difference in the type of modes of transmitter and receiver, I wouldn't expect to get a great deal more power. So this experiment is not really an experiment to do telluric transference of electric power using a TMT system, where the transmitter and the receiver coils are optimized to be Tesla transformers. Instead, it is a radio transmitter to a Tesla transformer receiver. Okay, good. I think really that's covered everything. Those are all the results we can get for today. And I will put the additional detail in the write-up. I will do a separate page on the design of the coil system. This coil is going to be featuring, it's going to have additional, let's just pan out so people can see the whole setup. It's going to have additional sections added to it when we go down to telluric transference of electric power at lower MF band or medium frequency. The other part also is there is no extra coil here, so Tesla also had an extra coil in his Tesla transformer system, and we'll also be doing some measurements and characteristics with the extra coil. The extra coil has a number of different characteristics. This is a straight secondary and primary transformer. Okay, so just in final summary for the this field experiment on the telluric transference of electric power and the Crystal Radio Initiative, is if we look at the frequency that we're working here, as well as the system being obviously from a broadcast radio transmitter to a Tesla transformer receiver, we're working at 909 kilocycles. So at that frequency, quite a reasonable amount of that power is going to get absorbed into the ground. That's what we've seen from telluric experiments that we were doing at 1.86 megacycles from the lab, is that at that medium frequency, mid to high medium frequency band, that the RF power doesn't travel very far in the ground, certainly not in the transverse mode. It will get absorbed into the ground a relatively short distance away from the ground system, and that also will contribute to the fact of the much lower received amounts of power. I mean, if we look at Tesla was working at frequencies down to 45 kilocycles, which is in the low frequency. So that also makes significant difference, so that we haven't got the longitudinal mode here. So the amount of power that could be transferred in this scenario at this kind of frequency, we would expect to be very low. And that's what we find today at around about 55 milliwatts into the tuned receiver at 909 kilocycles, 300 meters away from the transmitter mast that we can see here. Just to finish off, there's the top of the mast of the T antenna just above the tree there, and the main mast. So the things that are important, having a Tesla transformer at the transmit and the receive ends, getting a lower frequency as possible, and of course having for this experiment where there is the transverse mode involved, obviously one needs a big ground system as well in order to connect to the ground with the lowest possible impedance. Good. Okay, that's everything in summary from this field trip. I'll just show you the surrounding area. Is rather nice. That's the whole area surrounding Brookmans Park. There's the radio station itself. Great.